There is a wiring manual from 1943 that tells the reader how to repair this battery, and the instruction is to short-circuit it. Connect the terminals together, deliberately, and the cell recovers. That single line reverses everything you believe about how batteries work, and it is correct. The device is a stone jar holding copper, zinc, and blue vitriol, and it produces 1.107 volts without sagging. It powered the telegraph network of the industrial world for roughly a century. The first messages ever sent between continents traveled on jars like these. And when the world sat down to define the volt itself in the 1860s, this cell is what they measured against. About $70 builds one. By the end of this video, you will understand why leaving it alone is the only thing that can kill it. Let us dive in. Almost every battery you own is being damaged right now by doing nothing. Take the lithium cell in a power bank, sitting in a drawer at full charge. Chemistry keeps working inside it, whether anybody draws current or not, building up layers on the electrodes that were never supposed to form. Warmth speeds that up. A high state of charge speeds it up further. The pack you charged and put away for safekeeping is degrading faster than the one somebody uses every day. Now the alkaline cell's in the torch at the back of a cupboard. Nobody has switched that torch on in 3 years, and when they do, the cells have leaked. The potassium hydroxide has crept out through the seal, crystallized across the contacts, and eaten into the tube. The battery did not merely die, it destroyed the device it was living in. Then, lead acid. A car battery, left standing through a long winter, or a spare on a garage shelf, gradually forms hard sulfate crystals on its plates. Left long enough, those crystals stop responding to a charger at all. 3 unrelated chemistries, 3 different manufacturers, 3 completely separate failure mechanisms, and the same pattern underneath every one of them. Sitting still costs more than working, which lands badly on exactly the equipment you most want to trust, because emergency supplies are, by definition, the things nobody touches. The torch, the radio, the spare pack, the backup bank, every one of them is being stored, and storage is the condition that harms them. So an entire maintenance ritual has grown up around fighting that. Rotate the stock, check the batteries every spring, top up the charge every few months, replace them on a schedule whether they were ever used or not. None of that maintenance improves the battery. All of it exists to slow down the damage caused by owning one and leaving it alone. Reliability and dormancy are pulling in opposite directions, and in every chemistry on that list, dormancy is winning. For roughly 100 years, the telegraph network of the industrial world ran on jars of blue liquid sitting on shelves in back offices. Those cells were not spares, they were not stored, and nobody was saving them for an emergency. They worked continuously, holding a line open day and night in railway signal huts and telegraph rooms and station offices across 2 continents. An operator did not charge a battery. He maintained one, topped up the water, watched the levels, added crystals when they ran low. The relationship was closer to keeping an oil lamp burning than to filling a fuel tank. And it was so thoroughly ordinary that wiring manuals were still printing the maintenance procedure in the 1940s, more than a century after the design first appeared, as a routine job number alongside instructions for domestic lighting circuits. So there is a category of battery that spent a century in continuous service, in unheated buildings, tended by people with no particular training, and nobody thought of it as remarkable. What kind of cell gets better the more you use it? A voltaic pile is a good battery for about an hour, and then hydrogen ruins it. Volta's original stack of zinc and copper discs produced current, and it produced it reliably enough to launch a century of chemistry. What it could not do was keep going. Within minutes of connecting a load, hydrogen bubbles begin forming on the copper face and clinging there. Gas is an insulator. As that layer builds, internal resistance climbs, the voltage sags, and the cell strangles itself. Engineers called it polarization, and it is the reason the voltaic pile stayed a laboratory instrument rather than becoming infrastructure. Nobody builds a telegraph network on something that fades before lunch. Daniel's solution was to stop using 1 electrolyte and start using 2. Copper sits in copper sulfate. Zinc sits in zinc sulfate. Because the copper side is surrounded by copper ions rather than acid, no hydrogen forms there at all. Instead, copper ions come out of solution and plate onto the electrode as solid metal. Read that again, because it is genuinely strange. As this cell discharges, the copper electrode gets heavier. The zinc dissolves, and the copper grows. Nothing accumulates on the working face to choke it. That leaves one engineering problem, which is keeping the two solutions apart while still letting ions cross between them. Daniel's first answer was a porous, unglazed earthenware pot. Ceramic, fired without a glaze, so the wall is riddled with microscopic passages. Sulfate ions pass through freely. The two liquids do not mix. That stoneware jar became the standard form of the cell for the next 60 years. Then, in the 1860s, a Frenchman named Calode removed the barrier completely. His observation was that the two solutions have different densities. Saturated copper sulfate has a specific gravity of about 1.1985. Zinc sulfate is lighter, and it floats. Put both in the same jar, and they separate on their own, holding a visible boundary between them with no membrane at all. So the layout became simple enough to sketch in 10 seconds. A copper plate flat on the bottom of the jar, buried in copper sulfate crystals. A zinc electrode shaped like a bird's foot hanging near the rim, up in the lighter layer. Often a film of oil floating on the surface to slow evaporation. Removing the porous wall dropped the internal resistance, which meant more current from the same materials. That version, the gravity cell, is what the telegraph ran on. The output is 1.107 volts, and it holds there through continuous operation rather than sagging away. Daniel called his invention the constant battery, and the name was a claim about behavior rather than marketing. One more feature came free with Calaude's design, and it turns out to matter more than anything else here. That boundary between the blue layer and the clear layer is visible through the wall of the jar. You can see the condition of this battery by looking at it. In 1831, a meteorologist named John Frederick Daniel was appointed the first professor of chemistry at King's College London. 5 years later, he built the battery that made the electrical century possible. He arrived at it as an instrument maker rather than as a theorist. He had already won the Rumford Medal of the Royal Society for inventing a pyrometer, a device for measuring the temperatures inside furnaces. His interest was always in things that gave reliable readings. The first version of his cell, in 1836, was almost comically improvised. A copper cylinder, 3.5 inches across, serving as both the container and the positive electrode. A copper disc perforated with holes, set across the cylinder and recessed down from the top. Copper sulfate crystals piled on that disc to keep the solution below permanently saturated. And hanging down through a hole in the middle of it, a membrane tube made from ox gullet, holding the zinc rod and its acid. Ox gullet, the gut of a cow, used as a semi-permeable barrier because it let ions through while keeping the two liquids separate. Daniel noted himself, in his own description, that a porous earthenware tube would work in its place for practical convenience, at some cost in power. That substitution is the one the world adopted, and it is why these cells came to live in stone jars. The Royal Society awarded him the Copley Medal in 1837, its highest honor for the battery. Then it went to work. Daniel cells powered communications on the attempts to lay the Atlantic telegraph cable, the temporarily successful effort of 1,858 and the permanent one of 1,866. The first messages ever sent between continents were carried on current from copper, zinc, and blue vitriol in pots. And there is one further honor that outlived the technology entirely. When the international community first sat down to define electrical standards in the 1860s, they needed a physical reference for electromotive force, something reproducible that anybody could build and measure. The output of the Daniel cell is what they used. The volt was calibrated against a jar of blue liquid. One last detail, for its own sake. In 1883, a historian of the electric telegraph named Fahey found a Daniel cell pot lying in a field in Somerset. It had belonged to Edward Davy, who in 1837 and 1838 was racing Cook and Wheatstone to build a practical telegraph, and who then emigrated to Australia and left his apparatus in storage. Most of it was destroyed. A few of the pots survived, and that one sits in a museum today. The gravity cell did not merely power the telegraph. For a long stretch, it was what the telegraph ran on, everywhere. Collode's version spread because it was cheap and because it was better. Removing the porous pot removed the main source of internal resistance, which meant the same copper and zinc delivered more current. It also removed a component that could crack, clog, or need replacing. Picture the operating conditions honestly, because they are unlike anything sold today. Every cell open to the air, every cell full of liquid, every cell required to stand upright and undisturbed on a level shelf. Rows of them in railway signal huts, telegraph offices, and station back rooms across Britain, Europe, and North America, quietly holding lines open for decades. Now the detail that shows how deeply this settled into ordinary practice. A wiring manual published by McGraw-Hill in 1943 still carried the maintenance procedure, not as history. As a numbered job listed under Telegraph Wiring Job 208, Gravity Cell, sitting alongside instructions for domestic lighting circuits and conduit runs. More than a century after Daniel's first pot, an apprentice electrician was expected to know how to look after one of these. The procedure itself is short and specific. The blue vitriol must completely cover the copper element, and enough water must be added to cover the zinc. Care must be taken that the crystals fall to the bottom and do not come to rest on the zinc crowfoot. As the cell continues in action, the quantity of zinc sulfate steadily increases. And when it becomes too dense above 1.15 specific gravity, the top of the liquid should be siphoned off and water added to what remains. Read the tone of that. It is not describing an experiment or a curiosity. It is a procedure for keeping a working machine running, written for somebody who will do it again next month. There is one line in that 1943 procedure that reverses everything a modern owner believes about batteries. If the blue line rises anywhere near the zinc, the manual says, the copper sulfate should be siphoned out, or the cell placed on a short circuit. Short circuit the battery, deliberately, as the repair. Every instinct you have about electricity says that is how you destroy a cell, start a fire, or ruin a device. In this chemistry, it is maintenance, and the reason is worth following carefully, because it explains why the whole technology behaves backwards. The boundary between those two liquids is not passive. It is being actively held in place by the cell doing its job. While current flows, the reaction consumes copper sulfate down at the bottom and produces zinc sulfate up at the top. Discharge is continuously pulling the blue layer down and pushing the clear layer up. The separation maintains itself, so long as something is drawing power. Stop drawing power and nothing holds it. Diffusion takes over, quietly, the way a drop of ink spreads through still water. The copper sulfate creeps upward. Given enough undisturbed time, it reaches the zinc. Copper begins plating directly onto the zinc electrode, and the cell is finished. So placing it on a short circuit forces a heavy current through it, which drives the reaction hard, which drags the boundary back down where it belongs. Which means the failure mode of this battery is idleness. Everything in your drawer degrades fastest when full and untouched. This degrades fastest when untouched and unused. The correct way to own one is to never stop using it, and a cell that has run continuously for 10 years is in better condition than one that sat on a shelf for 6 months. Nobody suppressed this technology, and nothing about its decline is mysterious. It lost, fairly and completely, to sealed cells that could be thrown into a bag and forgotten. Almost nobody wants a battery that must stand level in a tray, be topped up with water, and be watched for a rising blue line. Convenience won, and it deserved to. Be clear about scale before building one. A single cell gives roughly 1.1 volts at modest current. This is a continuous trickle for small loads, and it was never anything else. The telegraph ran on banks of them precisely because one is not very much. What the design offers, in exchange for shelf space and attention, is a cell that has no reason to stop. A stoneware or glass jar, a copper plate, a zinc electrode, copper sulfate crystals, and water. If you want the full build, the jar selection, the electrode shaping, the oil layer, and the series wiring, we put together a complete walkthrough covering everything here and more. The link is in the description below. Start at the bottom and work up, because that is genuinely how this cell is assembled. The copper plate lies flat on the floor of the jar. Its lead has to be insulated along its entire length, all the way up and out, because a bare wire passing through the upper layer will corrode and eventually give you a fault inside your own battery. Solder the connection, then sleeve it. Scatter copper sulfate crystals around that plate. They sit there as a reservoir, keeping the bottom layer saturated as the cell works. Fill the jar with water. Hang the zinc near the rim, up in what will become the lighter layer. The traditional shape is a set of splayed legs, which is where the crowfoot name comes from, and the geometry is deliberate. It presents a large surface without reaching down toward the copper sulfate. Then leave it alone for a day. The layers form on their own, blue at the bottom, clear above, with a visible line between them. Float a film of light oil on the surface to slow evaporation, which is what the telegraph offices did. Around $70 covers jars, copper, zinc, and chemicals for a small bank. Expect 1.1 volts from each cell and wire them in series for anything worth running. Now 5 rules. 1. Copper sulfate is toxic. It is a brilliant, attractive blue. It looks like something you might find in a bath shop or a sweet jar, and that appearance is the hazard. Keep it out of reach of children and animals, never near food preparation, and never pour spent electrolyte down a drain. It is seriously harmful to aquatic life. 2. This cell cannot be moved. The entire design depends on 2 liquids staying stratified by density. Pick it up and carry it across the room, and you have mixed your battery into scrap. It lives permanently on a level shelf. 3. Watch the blue line. That visible boundary is your instrument, and no other battery gives you one. It must never be allowed to climb to the zinc. 4. Keep a load connected. This is the rule that separates a cell running in 10 years from one ruined in 6 months. An open-circuit gravity cell is a gravity cell in the process of being destroyed. 5. Treat it as an open vessel, because it is one. Evaporation, creeping salts around the rim, and the occasional spill are all normal. It belongs in a tray, on a level surface. Somewhere a small blue mess is acceptable. This is a maintained battery rather than a sealed one, and everything about it follows from that. It gives roughly a volt per cell. It will not run an appliance. It cannot be carried or tilted or taken anywhere. It has to stand level, stay loaded, and be topped up with water when the upper layer grows too dense. And its electrolyte is a poison that happens to be a beautiful color. Those are not small conditions, and they are why sealed cells won. What sits on the other side of that ledger is a cell with no expiry date. Nothing inside it is waiting to fail on a schedule. There is no charge to leak away, no film building on an electrode, no countdown started at the factory. Keep the copper covered, keep the zinc wet, keep a load connected, and the reaction simply continues. Which is what makes it strange in a conversation about blackouts. This is not equipment you store against an emergency. It is already running, on a shelf, doing its small continuous job. A clock, a lamp, a radio, a sensor. When the power fails, nothing happens to it at all, because it was never charging and never waiting. John Frederick Daniell built the first one in 1836, with a copper pot and a length of ox gullet. The Royal Society gave him its highest award the following year. His cells carried the first messages between continents, and when the world needed a physical standard for electrical potential, they measured the volt against this jar. If discovering the practical, unglamorous corners of engineering matters to you, subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found. We will be tracking all of it as it develops. So tell me something. What is the longest running thing in your house, and has it ever actually been switched off? I read every single comment.